Hello, welcome to Maths with EJD. In this video, I'll be talking about the mixed strategy Nash equilibrium in the matching pennies game. In the previous video, I talked about matching strategy Nash equilibrium in the rock, paper, scissors game, and we saw the randomization of, the strategies of two players such that no player could actually predict what the other player is going to play. So this is going to be something similar to that, except that the game is different. So can we have an overview then? What is let's have an overview of the matching pennies game. So the matching pennies game is a classic two-player zero-sum game. Two-player zero-sum. Zero-sum game means that if one wins, the other loses. So -1 for one means +1 for the other. That's basically what a zero-sum game is, or 0-0 for both. And it's just like rock, paper, scissors, right? So if if the two players have rock, rock, that's 0-0. But if one player has rock and the other player has scissors, of of course, rock wins. So rock gets -1, and the scissors gets rock gets one rather, and scissors gets -1. So something's very similar. Hmm. So this game is a classic two-player zero-sum game. Okay, right? And then each player, talking about player A and player B, has two strategies. Each player has two strategies. Either so, when we talk about a penny, right, we're talking about something like a coin, and it has head. So we can talk about heads and tails. So heads T and tails, I mean heads H and tails T. So the payoffs are structured such that player A, player A wins if the pennies match. So I mean this is now different from the rock paper scissors game. So if the strategies match in rock paper scissors, they both tie and that they get 0-0. But here, to win a point, the pennies have to match. So the payoffs are structured such that player A wins if the pennies match, while player B wins if the pennies differ. Okay. Now let's see what the payoff matrix looks like in this case. Payoff matrix for this game. Payoff matrix. So we already know the rule of the game, so we can easily determine the payoff. So imagine that you have okay, as usual, you have something like this. So you have player A down here, player A, and for up there we have player B. So these are the activities for player B. These are the activities for player A. So for player A, heads, that's H. Then for player B, tails, that is T. Same. For player A, we have heads and tails, right? For player B, we also have heads, T, and of course tails. I mean heads, heads H rather, heads H and tails T. So all right. So here, just like we said already, if the coins match, the first player, player A, gets a point, and since it's a zero-sum game, it means player B has lost a point. So, but if they don't match, it means that player A loses a point and player B gets a point. Then head head is a match, head tail is no match. So now tail head, of course, means that player A loses a point and player B gains a point. And then tail tail means the match and player one gets a point and player A gets a point and player B loses a point. So that's what the payoff looks like. All right. So let's go ahead and talk about the mixed strategies. Mixed strategies. So here now, a mixed strategy assigns a probability. So since each player has options to choose from, so it means the way they choose the options will go it will be probabilistic. So there's no specific way. So a mixed strategy assigns a probability to each pure strategy. So what should have been a pure strategy will now will now have a probability assigned to it, and that's what leads to a mixed strategy. So in this case now, let first of all, small p be the probability that player A plays heads. Okay. Then automatically that would mean that 1 minus p is the probability. 1 minus p is the probability that player A plays tails. Okay. Then we can move on and also talk about the possibility for Q now. I mean, for player B, let's now say that player B, so let's say Q is the probability that player B plays heads, and that automatically means that 1 minus Q is the probability that player B plays tails. All right. So having established the probabilities for the mixed strategy, then we can move on to talk about the Nash equilibrium. So finding, finding, finding the Nash equilibrium, finding the Nash equilibrium. In this case, again, we just remind ourselves that in a Nash equilibrium, each player chooses probabilities that make the other player indifferent to their options. Just like we also saw for rock, paper, scissors. Indifferent to their options. So the expected payoffs for both strategies must be equal. Okay. So let's go for step one. So step one now, let's look at the expected payoff for player A. All right. So first of all, if player B plays, if player B plays Q heads, Q is the probability of playing heads, right? And 1 minus Q tails, Q heads and 1 minus Q tails. Okay. So that simply means that player A's player A's expected payoff for expected payoff, right? For playing heads will be such that expected payoff for A for playing heads would actually be, now we are talking about player B. So for player A playing heads now, see what it's going to look like. So we have all this. So this is player A playing heads. So the expected payoffs, right? Um, so for player A here would be, Q, this is 1, and then this other one is -1. Okay, that's for player A now, 1 and -1. So that simply means that the expected payoff for playing heads for player A is just expected E sub A of H, and that will simply be equal to the probability of playing head multiplied by 1 plus probability of playing tail multiplied by -1. That's what the payoff would look like. So we have Q, all right, Q. Okay, we can have that's Q like 1 minus Q like this, something like this, because we can bring this -1 in front. So that's Q minus 1 plus Q. And all that will be equal to 2Q minus 1. So that is the expected value of A for playing heads. Okay. No matter what B plays now. So that goes. Now, number two. So the second one here is now okay. Okay, still on this, right? Still on this. So if player B plays Q heads and 1 minus Q tails, so player A's expected payoff for playing heads will be this. So still on player A now. So we also know that player A's expected payoff for playing tails, for playing tails will be such that we have expected uh, payoff for playing tails for A is equal to, now let's go to the table and see that again. So what is simply saying is that whatever player B plays, all right, so look at what happens to player A. So here player A gets either -1 for playing head and 1 for playing tails, So I mean, whatever player B plays, right? If player B plays head and player B plays tails. So if all player A is focused on his tails, right? So the first payoff is -1. Player B loses a point, and the second one for playing tail. I mean, for playing tail when player B plays head, the payoff is -1. That's a loss of 1. For playing tail when player B plays tails, that's a payoff of 1. That's -1 and 1. Basically, that's the idea there. So for this now, we are going to have the probability of playing a head in this case now is Q multiplied by the -1 that we get when player A plays tail after B had played head, right? So Q into -1 plus 1 minus Q into 1. That's the payoff for playing tail when B also had played tail. So that means we have minus Q, all right, plus 1 minus Q. And that is simply, uh, okay, yeah, this is minus Q plus 1 minus Q. That is simply 1 minus 2Q. So this is EAT. So this is also important, right? So E of AT is 1 minus 2Q. In the other case, E of AH was 2Q minus 1. So that goes. Now, we have this indifference condition. Okay. So let's do that. Going by the indifference condition, going by the indifference condition, this is a condition at equilibrium. Going by the indifference condition at equilibrium, we know that EA of H should be equal to EA of T, basically. And if that is the case, EA of H is 2Q minus 1. So we have 2Q minus 1 equals EA of T, which is 1 minus 2Q. 1 minus 2Q. So if we put all that together, we have 2Q plus 2Q, this coming here, equals 1 plus 1. That means this coming here. So we have 4Q equals 2. So that means 4Q over 4 is equal to is equal to 2 over 4. So this cancels out. And Q is equal to 1 over 2. Okay? Q is 1 over 2. So it means that the probability of playing head or tail is basically 1 over 2 because 1 minus Q will also be half, right? So we have that sorted. So that is step 1, focusing on expected payoff for player A. Okay. So let's go for step 2. Step 2 now, exactly the same thing is going to happen. So we have expected payoff for player B. Expected payoff for player B. Exactly the same thing is going to happen. So here, point 1. Okay, that is, we did point 1 here. This should actually be point 2. This condition now is point 2. It is actually point 2. So this is like our point 2 here, where we invoke the indifference condition. So point 1 here, if if player A plays P heads and 1 minus P tails, what happens? First scenario, we have, okay, let me go blue. So first scenario, we have the player B's expected payoff for playing heads will be as follows. That's expected value, expected value for B, expected payoff for B for playing head now. So let's look at, so we have to go back to the table to see that. So now whatever A plays, we want to see what happens to B for playing head. So let's see that. Okay. So let's go to the payoff matrix. So now our focus has shifted to, so whatever A plays, what happens to player B? So imagine this is A A playing both head and tail. Okay, this should go. Okay. So this is A playing head and tail, right? So when A plays head and tail, what happens to B for playing head. Of course, we know for B now, for playing head, that the payoffs are -1 and 1 for B. For playing head, when A, whatever A plays. So the two situations are -1 and 1. Those are the two payoffs for B. So in that case now, we have the expected payoff for playing head. That'll be P, which is -1 plus, all right, plus, is it -1? Is it -1? Let me see. The first one is in -1. Yeah, it's -1. Head to head, that's -1 for B. And then tail to head, that's 1. Okay, good. So that's -1. So that's P, probability of playing head, that's -1, multiplied by -1 into 1 minus P multiplied by that 1. So we have minus P plus 1 minus P. And that is 1 minus 2P. Okay, so that means the expected payoff for B for playing head is actually 1 minus 2P. So this is taken care of. And then we have the other one. So we have the other situation, which is that player B's expected payoff for playing tails will now be expected payoff of B for playing tails. So let's go back to the table and see what we have there. So whatever A plays and B now plays tails, let's see what happens to that. Okay. Right. Now, whatever A plays, and if B plays tails, what happens? So as we can see, right, we have again, we have 1 and -1, corresponding to those probabilities. So 1 and -1, 1 for tail, -1 for playing, 1 for head rather. Okay, when player A plays head and B plays tail, B gets 1 point. When player A plays tail and player B plays tails too, B gets -1. So that's basically 1 minus 1. So 1 minus 1. So we can come for that. So EB of T now is probability of playing a head multiplied by 1 plus probability of playing a tail multiplied by -1. So we have P, all right, P into 1 minus 1 into, or better, minus 1 minus P like this. So the minus does bring it forward. So because we are multiplying, so that is P -1 plus P. So that is 2P minus 1. So this is expected payoff for B for playing tail. So we have this. Okay. So again, we continue to the second step. I mean, the second point under step 2, right? So 2 now, we now set EB of H to EB of T. And what is this? This is basically the indifference condition. Indifference condition for equilibrium. Indifference condition for equilibrium. Okay, just like we did before. So what is EB of H? EB of H is 1 minus 2P. EB of T is 2P minus 1. So we have, so this now becomes 1 minus 2P equals 2P minus 1. So you can add, bring -1 here. So you have 1 plus 1. Bring minus 2P here. You have 2P plus 2P. And that will be 2 equals 4P. So we have 2 divided by 4 equals 4P divided by 4. 4 cancels out. So we have P equals 1 over 2. So again, we have P equals 1 over 2. Of course, 1 minus P will automatically also be 1 over 2. So finally, can we talk about the results? So the what do we have now? The mixed strategy Nash equilibrium. What is that? Mixed strategy Nash equilibrium as we conclude. So we see that both players play each strategy with equal probability. Okay, that means that P is 1 over 2 for player A, as you have found, and P and Q also. Q is also 1 over 2 for player B. So what this does again is this ensures no player can improve their expected payoff by unilaterally changing their strategy. So again, with this, we've come to the end of this mixed strategy Nash equilibrium for the matching pennies game. And it's somewhat similar to what we found for the rock paper scissors game. So we have an element of randomness such that nobody can predict what a player is going to do. So because there's equal chance of going any of the ways. So after now, I'll be talking about, I think, extensive game forms. I think that'll be the next set of things I'll be considering. So if you have not subscribed to this channel, you want to do yourself a lot of good by subscribing right away, and of course hitting the notification bell so you can always get alerted each time a new video is released. And don't forget to comment. Let me know if you want me to teach a topic or solve a problem, and like and share so that more people can have access to this great learning. Till I come your way again, play the games of life with wisdom. Bye.